Good evening. I'm Mehmet Ansoy. We are today honored to have a guest speaker, Dr. Ryan French, who is a solar physicist working at the National Science Foundation's National Solar Observatory, also science communicator and an author. Since completing his PhD 2 years ago, he is pursuing the mysteries of the sun at the forefront of modern solar physics research, using cutting-edge telescopes on the ground and in space. Ryan also works to share the wonders of the sun and space with the public through social media, public talks on television and radio. And last Monday, he was the co-host of the National Science Foundation's live stream of the total solar eclipse in Dallas. So please welcome Ryan for his talk.
Well, I got 2 calcium today. Should have checked.
Screen. Okay, how's that looking? Okay, so the camera's here, you guys are here, but I'll be changing slides on this laptop, so there might be a little bit of jumping around. But hello, everyone. Hello to everyone online as well. It's a pleasure to be here. Thank you much for the kind introduction. And today we're going to be talking all about the mysteries of the sun. Okay, so we're all familiar with the sun. We see it in the sky every day, right? To our eyes, it seems constant, seems unchanging. If you didn't know otherwise, you'd think the sun was uniform, always remaining the same, right? But this is not true. If anyone saw the eclipse last week, and I know a lot of you did, and we'll talk a bit more about that, we know that's not true because we can see with our eyes structure and variation in the atmosphere of the sun. And relating to that, this year in particular is a very big year for the sun and structure and evolution on the sun for 2 reasons. Firstly, this year is solar maximum, and I'll talk about what that means for anyone who's unfamiliar. But this year is basically the peak of the sun's activity cycle, and the most active the sun will be for another 11 years. That's happening this year. And similarly, last week we had a total solar eclipse. It's the last one in sort of continental USA until 2044, so 20 years. So really fortunate to have that going on relatively close to where we are here. Okay, so we're going to begin our journey quite far back in time, back in the year 1128. And if possible, I want everyone to use their imaginations here a little bit, and maybe even some participation if you're feeling up for it. I want everyone to close their eyes for a moment. Close your eyes. And imagine that you are not here in Denver in the year 2023. You are instead living in the English town of Worcester in the year 1128. And you are a monk. You wake up one day on this morning, 1128, doing whatever it is that a monk would typically do at this time. And you walk outside. Now, the sun has just risen, so the sun is low in the sky, and it's foggy, it's misty. So the sun is not immediately super bright as you look at it, to the point that you can actually look at the sun very briefly without damaging your eyes. And when you do that, if you open your eyes, this is what you see, this image here on the right. So using your imaginations, if you are a monk in 1128, you don't know anything about the sun, what do you think these objects are? Do you see these big black objects in the atmosphere or the surface of the sun? What do you think? Anyone got any suggestions? No.
Sunspots.
Well, I think if you were a monk at 1128, that would have been quite a leap. quite a leap. They are sunspots. That is correct. It's got the measles. Sure, you're writing this up. There's a hole in the sun, a big a tunnel in the sun, I think. I almost think they almost look a bit like sea urchins or something like that, sort of stuck to the side of the sun. But whatever their interpretation was, we won't actually ever find out, because this image was recorded in a very long document. It was about 700 pages of English history. It's called the Worcester Chronicles. It was recorded by these monks. And this book spanned hundreds of years, about 400 years of history. And in the whole book, there are just 5 images. So there was 3 depicting scenes from the Bible. There was a picture of the coronation of the king and this. So out of all these hundreds of years, they clearly thought this was significant enough to write about and to draw about. There was even a total solar eclipse the year before. They didn't even draw the eclipse, but they did draw this. So clearly, even then, they knew what eclipses were, but this was something new and alien to them. What they had observed for the first time, as you correctly point out, are sunspots. These are the first recorded observations of sunspots on the sun. And so here's a bit of a zoom in, here on the left, here on the right. Left is their sketch of the sunspot. On the right is a relatively modern, still quite old, observation of a sunspot. And you can see, even with just their eye through the cloud, unmagnified, they were able to see a lot of information. They've got the dark middle part of the sunspot, which we call the umbra, and sort of the lighter, sort of fuzzy fan-like penumbra as well, which I think is amazing that they could see 2 of these just with their eyes. And even today, there are sunspots that occasionally are big enough just to see with eclipse glasses. So without a telescope, you wear the eclipse glasses, you can see small sunspots. But to be able to actually see this structure, these sunspots must have been really, really large, much larger than any that we've had in recent couple of decades. But the next sort of round of sunspot observations came in 1610. No surprise, 1610 was around the time that telescopes were starting to be used for astronomical observations. And as soon as they started having these observations of sunspots, people had all these wacky theories about what was going on. They had observations of these things changing day by day. They were starting to see the sun rotate via these sunspots. These observations, by the way, again, they didn't have special solar filters. They were pointing their telescopes directly at the sun. And, you know, the telescopes they were pointing at the sun, it wasn't a 20-inch Dobsonian, as you mentioned earlier, obviously, because that would probably burn a hole in the back of your head. They were small sort of 1-inch lenses. They would do it low in the horizon, but still kind of miraculous that they didn't get any permanent damage to their eyes from doing this. But the first astronomer to sort of give a punt at what these were was a German astronomer called Christoph Scheiner. And he didn't think these were actually related to the sun at all. He thought these were actually planets that were orbiting closely to the sun, and we're sort of seeing the transit of these small objects in a similar way to how we see the transits of Mercury and Venus. He was wrong, unfortunately, but his sort of method of doing this, you know, it wasn't completely insane. Even today, the way that we observe a lot of exoplanets is by measuring the drop of brightness as sort of planets pass in front of them. So, you know, maybe he was a bit ahead of his time with some of these ideas, but he was very wrong in this case. And he was proven wrong by Galileo himself, the guy who started using the telescope to point at the sun, who said, no, these are definitely orbiting with the sun. I've shown that these are all moving as the sun is moving, but he thought these were sort of cloud-like structures in the atmosphere of the sun. And you can sort of understand why some of the things that you'll see on this list are what they sort of proposed. They're sort of equating their earthly experience and the things we see around us here on Earth. They were equating that to try and sort of say what was going on with the sun. So he said these were big clouds that were floating. But this Christoph Scheiner guy, he came back and said, no, you're wrong, Galileo. Probably a bit embarrassed about being proven wrong the first time. He said, these are not clouds in the atmosphere. These are sort of dense objects sort of in the surface. So more analogous to islands in an ocean than clouds in the sky. Again, he was wrong, but you can kind of see where he would get some of these analogies, thinking these were almost big continent island things that were floating or moving around on the sun. And next up, bit of a time jump now. We're now at about 1801, William Herschel. William Herschel, very famous astronomer. He was president of the Royal Astronomical Society in the UK for a while. He also was the astronomer credited with discovering the planet Uranus. So he discovered an entire planet, did a bunch of other really cool things. And he said, sunspots are openings in the sun's luminous atmosphere, allowing a view of the cooler underlying surface of the sun. Now, this is correct in many ways. Sunspots are colder than the rest of the sun. He was able to deduce this. And they are sort of slightly, you're seeing slightly lower down in the atmosphere of the sun as well. So he got that right. But unfortunately for him, he didn't stop talking. You can see I've blurred out the end of the quote here. Because what he actually said was that sunspots are openings in the sun's luminous atmosphere, allowing a view of the cooler underlying surface of the sun, which is likely inhabited. So this is a verbatim quote from William Herschel, who thought that there were aliens living on the sun, or at least in sunspots on the sun. So I think this is a nice little lesson. You can be very accomplished, very right about some things. He discovered an entire planet, but embarrassingly wrong about other things. And people will remember what you do right, not what you do wrong. So I think that's a nice life lesson there. Okay, but moving on now to the solar cycle. So I briefly mentioned that at the moment we are at the peak of the solar cycle, but what does that mean? Well, around 1840 or so, so around number 8 sort of labeled on this graph going across. Oh, I should say, by the way, what this is. This is just time on the x-axis, year. Each data point is a month. The black data point is a month and the blue is sort of a smoothed version of that. And on the y-axis, it's just the pure number of sunspots that were on the sun in that month. So just count all the sunspots that were observed, plot them like this. And so around 1840, a couple of astronomers, they started looking back through historic sunspot diagrams that people had drawn for decades. They just started counting the amount of sunspots that appeared in every single map. And when they sort of plotted the number of sunspots with time, they saw this really strange pattern, right? They found it was increasing, it was decreasing in a way that they sort of hadn't really seen or noticed before. And as it turns out, the cycle time is 11 years. So you go from 11 years where the sun is not really doing anything at all, no sunspots, basically sometimes a month at a time without sunspots, and then to the peak we call solar maximum, where you can have hundreds of sunspots every single month. So they discovered this cycle. They were originally doing this research to try and compare the solar cycle to like the price of wheat, which seems strange, but that is basically analogous for trying to see if the sun's activity can affect Earth's climate in any way. And they found that it didn't in this case that they were looking for. But yeah, certainly very, very interesting. So at the time, they were in solar cycle 8 or so by the time they made this discovery, and they sort of went back and labeled the start of the observations that they had as solar cycle 0. And right now we're all the way on the right. We're in solar cycle 25 and approaching the maximum of that, but I'll talk a bit more about that later on. Okay, but the sun got even stranger in the year 1859. So let's recap, right? We have these dark spots that we see on the sun. We see they move with the sun. We see they are colder. We see they are sort of denser regions, and we see they follow this 11-year cycle. So they just weren't putting it together. These were sort of islands, clouds. What could be causing this 11-year cycle? And things even got even stranger in this year, 1859. This man on the left, who I'll give a brief caveat in a minute, but there was a man called Richard Carrington, who was, not super famous at the time, but he had probably what I would consider as a dream Colorado job combination. Maybe someone here even has this job combination, because he's a part-time astronomer and part-time brewer. So I think that's the Colorado dream right now, but he was in the UK at the time. And this actually is not a picture of Carrington. If you Google Richard Carrington, this is the picture that will come up. But this actually isn't him. This is actually a picture of Kelvin. So I can't find a picture of this man, which is really strange. Like, even on Wikipedia, this is the picture that is included of him. So really strange. But anyway, he was observing sunspots almost at sort of semi-professional level. It wasn't his full-time job, as I said, but he was observing sunspots to try and understand the rotation of the sun in certain ways. He didn't really make any big progress relating to that. But what he did see is on one particular day when he was drawing a sunspot, he noticed 4 bright lights. And I'll point here on the screen. They're labeled A, B, C, and D, just for those online. These 4 bright lights he saw within this sunspot. And he's been observing sunspots for years. He'd never seen anything like this. They weren't flashes. They didn't flash and leave, but they sort of grew and were there and then sort of disappeared over a minute or two, and then another bright light would appear. And he didn't know it, but he had made the first ever observation of a solar flare. First recorded observation of a solar flare. At the time, he didn't know what he had seen, but he recorded these, and it's fortunate that he recorded these as the way he did, because that night, sort of about 16 hours later, so imagine this was early morning in the UK, and then that night in the US, so about 16 hours later, North America saw the greatest display of the Northern Lights on human record. So here in Colorado, there are stories of miners in the mountains not far from here who were sleeping, and they woke up to what they thought was the sunrise and started getting ready for the day to walk outside and notice it was the middle of the night. And what they had mistaken for the sunrise was the bright green aurora directly overhead. So bright they had mistaken it for the rising sun. And the aurora was seen as far south as sort of south of Florida, even the Caribbean, even sort of Central America recorded seeing the northern lights on the horizon. But here in Colorado, it was very much directly overhead. So a really, really impressive event. And over in Europe, whilst North America was in nighttime, they were having equally weird phenomena in the daytime. Telegraph machines, which were the peak of technology at the time, these just started sending and receiving phantom messages. So no one was sending anything, no one was, some weren't even connected or turned on. And the machines just start receiving noises, sort of ones and zeros just start coming into the telegraph machines, and they had no idea why. And they were sort of fairly soon after this all happened, they put these three things together: the bright flash in the sunspots, the aurora, telegraph machines acting strange. So they sort of knew these were linked, but again, they had no idea how. How could a flash on the sun cause all this strange phenomena here on Earth? And the event today, it still bears his name. It's called the Carrington event. Okay, but the big discovery that sort of solved everything actually came in the year 1908. So again, a few decades after these previous discoveries. And these come from a man called George Hale, who was working in California at Mount Wilson Observatory. And he discovered that sunspots are magnetic. The picture or the sketch that he drew to confirm this is not particularly interesting. I've not shown it on here. But essentially what he found, that sunspots are just giant magnets sitting in the atmosphere of the sun. You might all recall back from school, this experiment on the left. You take a magnet, you sprinkle some iron filings, and the iron filings trace the magnetic fields. And that is essentially what's happening with sunspots. They're a big magnet, and you can almost start to see here coming out from the sunspot, these iron filings. This picture, by the way, is taken from the world's largest solar telescope. It's called DKIST, or the Inouye Solar Telescope. It's run by the organization that I work for, and it's 4 meters in diameter, which for a solar telescope is massive, because the previous biggest one was 1.5 meters. So some cool science coming out from this telescope. We know magnetic fields here on Earth. The Earth has a very simple magnetic field, has a north pole, has a south pole, and that's it. It gets a little bit compressed, sort of the further you go up away from the Earth, and sort of stretches out on the night side. But basically, at least close to the surface, we have a north pole and a south pole. The sun, however, is much more chaotic, because every sunspot that is sitting in the atmosphere of the sun acts as a north pole or a south pole. So you have a complicated web and network of magnetism that just spans the entire atmosphere of the sun. So a very, very complicated magnetic field. And this is where the origin of sunspots come from. It's from these regions of concentrated field. I should say, by the way, the reason sunspots are dark is because of this strong magnetic field. Basically, plasma that is sat within that region is basically essentially isolated from the rest of the sun. Sort of that field is repelling plasma. So it's sort of isolated so it can cool down to lower temperatures, because it's not touching sort of the heat from the rest of the sun. That's why we see it as being dark, because they're colder. Okay, so lifting up off the surface of the sun, the image I showed you before of a sunspot was an image taken in white light. But if you look at the sun in ultraviolet light, things look very different. So when you look at the sun in ultraviolet, the corona, or the atmosphere of the sun, glows really, really bright. So this here is an ultraviolet image. It's plotted in red here, but it's ultraviolet. It's a color we can't see, so I could plot this in any color, really, just to demonstrate that. And you can see these bright patches now. These are those regions of intense magnetic field above sunspots. So above these sunspots, we now have the hotter atmosphere, and you can see, hopefully, sort of stretching between these bright regions, it looks like that iron filings experiment that I showed you before. You can see the plasma, in this case, arching between different magnetic poles here on the sun. And this leads to some cool stuff. And this is actually what I work on. So I work on a phenomenon on the sun called solar flares, which are essentially an intense and very rapid conversion of energy. So in this magnetic field on the sun, as the sun moves around and the magnetic field twists and tangles, you can get sort of a very big buildup in what we call magnetic potential energy. What does this mean? Well, some of you might be familiar with a concept called gravitational potential energy. If I lift up this water bottle, I have increased or changed the chemical energy of my body. I have increased the gravitational potential of this bottle. And what does that mean, gravitational potential? Well, it means if I let go, that potential is then converted into another form of energy. And the same thing is true on the sun. As these magnetic fields evolve, you have a buildup in magnetic potential energy, which is energy waiting to be released. and it gets released in many different ways, but one of which is a solar flare. So the magnetic fields essentially break, they snap, and that energy is converted from the magnetic fields to light, mostly UV, X-rays, the acceleration of particles to almost relativistic speeds in some cases, the heating of plasma, the ejection of material as well. So a really sort of explosive dynamic process. These are two fairly famous solar flares from 2017. They were both from the same sunspot region, 4 days apart. So one happening just there on the left and one happening on the very edge of the sun. And these are the two largest flares since 2003. So two very large recent flares. And I've done a fair bit of work on this flare on the right in particular. Okay. Next slide is something very closely related to flares, but independent. It's called a coronal mass ejection. Where does this name come from? Well, it's the ejection of mass of stuff from the sun's atmosphere, which we call the corona. So this is different to a flare, which is particles and light. And this is the ejection of sort of bulk, massive amounts of plasma, which hurl out into the solar system. This is that same flare from September 2017. The fuzzy stuff you see hitting the camera, this is actually particles hitting the detector. So just creating noise on the camera there. And you can see the eruption firing off from the right. I have some other movies. One here on the bottom left. These things are much slower than flares. Flares are light. They travel at the speed of light. These are only, quote unquote, only travel at about 2,000 miles per second. So still very, very fast, but much slower than the speed of light by about 100,000 times or so. So these take a while to reach us. And this really was the missing link that they didn't know about back at the Carrington event. He saw the flash of light on the sun, which was the solar flare. They saw the influence of that arriving at Earth, but they didn't have the missing piece, which was the actual eruption of physical stuff that was leaving the sun and traveling throughout the solar system here. And it's unfortunate, actually, because the year after that Carrington event, back in 1860, there was a total solar eclipse. And someone had drawn in that eclipse sketch, very clear when you know what you're looking for, an eruption from the sun was mid-progress in that eclipse. And it was very visible in the sketch, but they didn't know what they were at the time. So they had no context for what they were seeing, really. This next one gives a bit of a different view. This is real data. Again, all these are real images here. This was taken by a spacecraft called Stereo. So Stereo is a spacecraft that's not orbiting the Earth, it's actually orbiting the sun. So in this case, it's looking at the sun on the left, that small orange dot, and Earth is just out of frame on the right. So you can actually see the material moving from the sun to the Earth. And you can see Mercury is just on the edge of this edge of the red frame here, the red circle. And you can see that eruption leaving the sun. That's a coronal mass ejection. You can see it traveling through the solar system. Mercury immediately, and I'll restart this here. Mercury gets absolutely bombarded by this thing just there. Mercury getting absolutely smacked around silly. And Earth just out of frame here on the right as well. So we can see these things traveling through the solar system. This next slide, this is not real image, you'll be pleased to know. This is just a diagram. The sun doesn't even look like that. And if the sun was that close to Earth, we wouldn't be here right now. But it gives a bit of an idea as to what actually happens. This plasma, these eruptions, they leave the sun, they travel through the solar system, and as they arrive at Earth, thankfully we are protected. We have a big magnetic field which deflects the worst of the stuff coming from the sun. It's not quite that simple. As we all know, north and north magnets, they repel, right? And north and south magnets, they attract. If this stuff coming from the sun carries with it a magnetic field that's sort of pointing north and the Earth is pointing north, they repel. They sort of flow right past each other, nothing happens. But if it's coming from the sun and the magnetic field is opposite to the Earth, then now they're actually going to interact. They're going to sort of combine. And as this happens, high energy particles from the sun can enter the Earth's magnetic field because they've sort of just attached to each other. And the high energy particles travel down the Earth's magnetic field. And I'll just use my mouse here. They travel down the Earth's magnetic field and they collide with the upper atmosphere of the Earth. When we have these high energy particles smacking into the top of the Earth, it causes the atmosphere to glow, and that's how we get the aurora, the northern lights. And that's also why the stronger the eruption from the sun, the further back, in a way, this eruption is able to peel through the layers of Earth's magnetic field. So the further in you go, the further south you then connect with the atmosphere. So when that aurora was seen here in Colorado back in 1859, that really was a very powerful eruption to peel back through all these layers and give the aurora this far south. So yeah, really cool. The stuff coming from the sun, and we can see this manifesting in the form of this beautiful light show. But it's not all pretty colors in the sky, although a lot of it is pretty colors in the sky. If you recall, back in this 1859 event, telegraph machines were going crazy in Europe. How could this be? Well, there's something in physics, it's got a bit of a boring name. It's called Faraday's law. This is essentially the idea that if you change the magnetic field over a conductive material, you create an electrical current. This might sound quite abstract. If you have a wireless charger, my watch uses a wireless charger, and my MacBook sort of has these mag chargers. This is how they work. They change the magnetic field, or in this case, sort of the other way around, but they change the magnetic field, and that creates a current and charges your device. This is a concept we're all familiar with. But as this thing is traveling from the sun to the Earth, it has with it a magnetic field. So as this passes over a satellite, for example, you can create an electric field in that satellite that satellite might not be fit to equip or to sort of hold. Same on the ground with power grids. If you have a power grid that has a capacity of a certain amount of electricity, and you have this big eruption that creates an electrical current in this power grid on top of the one that's already there, there's a potential to overload transformers. You might have sort of regional power outages, things like that. And the sort of umbrella of these effects are sort of colloquially named space weather. So this is weather not here on the ground, but weather sort of coming from space. And there are a few different impacts of space weather. It's listed in the National Index of Natural Hazards, I think is the term here in the United States. And as you can see, there's lots of different industries this can affect. And the worst case scenario for this, there are often people online that like to say it's going to be an apocalyptic doomsday scenario. That is not the case. But the worst case scenario, which we consider to be similar to this event back in 1859, is as many, this is a worst case, as 20% of satellites could stop working. They're not falling from the sky, just like onboard electronics might stop operating. So certainly a disruptive natural disaster, and could cause a similar amount of financial damage as sort of the worst earthquakes and volcanoes and tsunamis and stuff like that. But critically, with no direct threat to human life, just some sort of midterm financial disruption. I mean, we all lived through COVID, right? It wouldn't be as bad as that by a long shot, but certainly something that is worth understanding. And scientists like myself are working to understand these eruptions on the sun, how we can predict that, and how we can mitigate the potential effects of this. So as technology improves, forecasting improves, power grids and stuff become more robust, the risk of this is diminishing every year, but there are still reasons to look out for this. A couple of recent examples back in 1989, not that recent, but it's the most recent case of a power grid going out due to a eruption from the sun. This was in Quebec in Canada. About half a day, about a few million people, the east coast of Canada had no power. A transformer was damaged due to an eruption on the sun. And more recently, back in January 2022, Elon Musk, he launched a bunch of his Starlink satellites. We were talking about Starlink earlier. He launched, I think, 50 or 60 Starlink satellites, and he launched them in the middle of a solar flare. I don't know if he knew about solar flares or if it was, I don't know the story behind the scenes there, but he launched it within a solar flare. So 2/3 of his satellites didn't make it into orbit. They crashed. So they sort of started taking a bit more seriously there. But there's another recent example of why it's important to monitor these things. It's a spectrum, right? There are small scale impacts and much larger impacts as well. So I mentioned this year in particular is an interesting one. That is because we are predicting this year to be the peak of the solar cycle. So solar cycle 25, we can see here on the right, I think this goes up to February or March. Yeah, okay, so that last data point on the right is February. And so you can see we're already more active than we were back in sort of 2014, but we don't know how high we're going to go this year. We'll see, potentially an exciting time. But what does this mean? If it's solar cycle, peak of the solar cycle, what does this mean to you? Well, it means we'll have more sunspots on the sun, more solar flares, more eruptions on the sun due to that. And as a result of this, as well, more Northern Lights shows. So expect more incidences of the Northern Lights being further south and accompanying news stories relating to this. This picture on the right is one I pulled off Twitter This was from April 2023. Last year, there was a large solar eruption. We had quite a large solar storm. That is Estes Park in Colorado. So that is the Northern Lights were seen here from Colorado. Again, probably not to your eye, but to a sensitive camera. You can see the high altitude red emission there, which I thought was pretty cool. I did actually dragged my wife Georgie quite late to try and see the Northern Lights. We didn't see it, so maybe it was a waste of time for me, but I'm glad some people managed to spot it here in Colorado, which is very cool. And also expect more news stories about the sun. Some of these will be accurate, some of these will not be accurate. There have been many news stories in the last month about potential apocalypses due to solar flares. There was a case a few months ago. A bunch of cell towers went down for an unrelated reason, and people were trying to attribute these to solar flares. Just expect more news stories, not all of which will be correct. These news stories tend to correct themselves in the days afterwards, but when these things are first released, sometimes they don't quite get some of these stuff right, because it's quite an abstract topic and quite different to sort of regular weather impacts that these sort of journalists normally talk about. So I thought we'd finish off just talking about the eclipse last week. I'm curious, this goes to folks online as well. I'd love to know who saw the eclipse, either a total eclipse or saw a partial from here, or who didn't see it. I guess I'll start with who didn't see it. Did anyone not see any eclipse? Okay, cool. Who saw a partial eclipse, maybe from Colorado? Again, did anyone travel to see the total eclipse? Out of all you folks, did anyone go somewhere other than Texas? Or did most people go to Texas? Where did you go?
Missouri.
Southern Missouri. Cool. Certainly, I was blown away. It was actually my first solar eclipse. First time in totality. I was down in Dallas, just down here. I felt like I understood the physics of the corona like so well, having done it for years. But it's the first time seeing it with my eyes. It was quite an emotional thing, sort of to get that emotional response. But yeah, certainly very, very cool. Couple of pictures I took. This is not coming up very well on the big screen here. I got some nice images of the partial phase. There are some sunspots that I can see on my screen in these big ones. Unfortunately, in totality, as I'll show on the next slide, I was actually on camera for the portion of totality. So I tried to set up my camera to automatically take a photo, but the focus was off, sadly. So my totality photos are out of focus, but I saw it with my eyes, which I guess is the important part. This is what I was doing, which was mentioned briefly before. The National Science Foundation, which is, I guess, the company above the company that I am currently working at, they did an eclipse live stream. It was their first one. They were quite optimistically hoping to rival the NASA live stream. NASA have a lot of resources, which we didn't have access to. But if you're interested in watching this, it's called The Science of a Total Solar Eclipse. It's actually a 40-minute, it's about an hour. It's a documentary. So it's not just watching the eclipse and talking about the eclipse. We talk about all the science that can be done with an eclipse, talked about scientists flying a plane along the path of the eclipse to maximize observations, talk about this telescope in Hawaii. So I'll just give this a little plug if anyone's interested. It's like an hour-long documentary, and I feature on site here in Dallas. The guy on the left, unfortunately, sucker, he was on the studio in DC, didn't even get to see the eclipse. But thankfully, I was here on the right in Dallas. You mentioned you're from Dallas. This is the Perot Museum is where we're based for that. So when's the next one? This is a fun little graph or fun little graphic that I saw recently. This is every state by state, when the last solar eclipse was and when the next total solar eclipse will be, excluding the 2024 eclipse, which followed that yellow line. And there's a few winners here and a few losers here. The last time us in Colorado had a total eclipse was way back in 1918. The last time there was a total eclipse. But the 2045 eclipse is actually passing right through the south of Denver. I'm not sure if it will cross exactly where we're standing, but it does pass through the south of Denver. That's the edge of the path you want to head down south. That's 21 years from now. Long time away. But there's a few big losers on here. I was drawn to Arizona. Their previous eclipse was in 1806, and their next one, 2205. So really far. But the biggest loser, I don't know if anyone can spot this. I didn't even notice it the first time I looked at this, is Delaware. The last time Delaware had a total eclipse was 1478. Anywhere in the whole state of Delaware. Even Rhode Island, which is smaller, I believe. Even Rhode Island had an eclipse in 1925. But Delaware getting really screwed over there with what, nearly 800 years between eclipses, which is insane. And here's a nice little graph showing how infrequently these happen. This is North America, the total solar eclipses. So pre-2024, there was one in 2017, and before that, the previous one was 1979. So I spoke to a lot of people who said, oh, but I remember seeing one at school in the 90s or whatever. These would have been annular eclipses or partial eclipses. There wasn't one in the US after 1979 until 2017. So really quite a big jump. This is this century. This is the centuries, sorry, 21st century. So we had 2017, we've had 2024, it's the year we're in now, yes. And the next one is 2044, which just touches, I think, the Dakotas and some of Montana. But this 2045 one is the one that's really going to be very impressive, passing all the way across a lot of people, a really wide path as well. And you might think this seems like an obscenely far away, but I recently came across a bunch of news stories from the 1979 eclipse where they were talking about 2024, like it was this big, far sort of future year that, you know, would never come. And here we are in 24. So remember, 2045, heard it here first. But thankfully, you don't have to wait till 2044 if you're willing to travel. Eclipses happen somewhere in the world every 1.5 years on average. So this is the next 10 years of solar eclipses, which equates to 8 solar eclipses. So we've just had number 1 there. Spain getting quite lucky with back-to-back eclipses, 2026 and 2027 in Spain. You can see numbers 2 and 3. There's one that goes through, you can just see basically straight across the Pacific Ocean. Straight through the Pacific Ocean is one of those as well. Australia getting lucky as well. They've actually got the ones in, where are we there? 2028, 2030, but also 2035 and 36. So Australia getting 4 eclipses in 8 years, which is really, really lucky for Australia there. So if you don't want to wait till 2044 or 2045 for it to go over your heads here, these are your next options, 2026 and 2027. So at the end of my talk, I welcome any questions. If anyone's interested, I've written a book on the sun. I have a few copies here that I'm willing to sign and then sell for $15. But yeah, apart from that, I welcome any questions. Thank you for your attention. I can take questions online as well.
I have heard this term and I've not been able to look it up, sadly. What exactly is relativistic speed?
The question online, if you can't hear, is what is relativistic speed? It's particles that are traveling close to the speed of light. So when a particle approaches sort of past 95% the speed of light, we call that relativistic, and weird things start happening to that particle. Sorry, it was probably a specific term that I didn't need to use, but yeah.
All right.
Yeah.
Brian, I guess question.
Sure.
This I photographed the whole sequence from down in Arkansas, and I saw something sticking out on it that I initially, I've only seen this one and the one from 2017. I saw some things recently that what I saw, the pink things like little pyramids and things sticking out are called solar prominences. Can you comment on what that is and how it compares to a flare?
I certainly can, yes. So I've brought up a little movie here. Let's see if I can repeat this. No, I'll just play this a few times. So this is the sun from the day of the eclipse. This is a telescope in space observing the sun in ultraviolet light. And this little object down here, this is what you saw in the eclipse.
Yes,
so
that's exactly it.
Yeah, that's exactly it. So this is it seen from space. So it's a prominence. They're also sometimes called filaments. And these are basically channels, almost like a slinky, sort of a slinky-like channel of plasma that is suspended in the atmosphere of the sun. So these are sort of rooted to the sun at one end, they stretch up and sort of connect at the other end, these big loopy things. The difference between a flare and an eruption, a difference between a flare and a prominence is a flare is a dynamic process. It's an explosive process that takes minutes to sort of hours, maybe on the longer ones. But prominences are long-lived. These can live on the sun for weeks, sometimes months at a time. So they're very long-lived events. They do in some ways look similar, at least in the wavelengths of light that you see in an eclipse. They can look similar to a solar flare, but the main difference is the longevity. These are much longer living things. There were a bunch of news stories actually that started calling this a solar flare. It's not, it's a solar prominence, but I hope you can agree, a very beautiful thing. And those who were at the eclipse, it was super, super visible and visibly red as well to the
Yeah,
eye.
it looked very much like the hydrogen alpha line.
Yeah, well, that's the emission. So, so hydrogen alpha is produced by a layer of the sun called the chromosphere, and these
Right.
materials are chromospheric material. So that was hydrogen alpha that you were seeing with your eye. Any red that you saw during that eclipse, so sort of maybe some red blobs, not quite the bright white Bailey's beads as they're called, but any red sort of blobs as well. That's hydrogen alpha that you're seeing. So the filter you use for your telescope,
Yeah.
see with your eyes.
Thank you.
Welcome. I've got a question in the room. I don't think people online can hear the people in the room, so I'll repeat the questions. That's about to be solved.
Right. Can you tell us about the research that is done during the solar eclipse?
Sure. So solar eclipses offer a unique opportunity to measure the sun's atmosphere, the corona. So normally if we want to measure the corona of the sun, it's very, very difficult to do from Earth. We can go to space and we can observe in ultraviolet light, like this movie here, tells us about the corona. Or in space, we can build, they're called coronagraphs. So you block out the sun and you can look at the sort of atmosphere around the sun. These are expensive. Going to space to research the corona, super, super expensive, right? But during a total solar eclipse, the cosmic alignment produces the corona for you. So instead of going to space, you can observe the corona here from the ground. So it just means that science experiments to research the corona are much cheaper, much easier than having to send something to space. So it's a lot more numerous. So there were events measuring the spectra of the sun, trying to understand why the sun's atmosphere is super hot, which is an ongoing problem. There were other research projects looking at active regions in the sun, trying to understand how these form and why these are the way they are. So there was a bunch of different experiments. Most of these are relatively small. We're talking 18-inch telescopes that were carried on planes to places like Mazatlan in Mexico or down in Texas. Our crew actually had one in Mazatlan, Mexico, and Illinois, Carbondale. We had a telescope up there. There was also a bunch of telescopes which are super cool that can fly on jets. So I was involved in one project called ACES, but there was a couple of different ones. You strap a telescope to a plane and it flies close to 50,000 feet, about 48,000 feet, and they fly along the path of totality. They can't quite outpace the corona of the sun, the path of the moon during an eclipse, so they can extend the observation period by about factor of 2. There was a case back in Concorde era where the Concorde can actually fly faster than the shadow of the moon. So the longest eclipse observed by someone on record in human history, because nothing's ever been faster than a Concorde, were the pilots on that Concorde plane that observed the full eclipse around an hour and a half, because they just followed the path of that moon, which is really, really cool. Yeah, great. Yes, at the back.
What does the latest research show about what's the difference between the corona and the surface of the sun?
Yeah, so the sun has a few different layers. You can sort of peel through them. The surface of the sun we call the photosphere. This is the surface that we see with our eyes, or the sunlight that reaches us is the photosphere. And if you look with a white light solar telescope and you see sunspots, that's what you're seeing, the photosphere. Above the photosphere, we have sort of a middle layer. It's called the chromosphere. This is what we observe with H alpha. If you have a H alpha telescope, this is cooler than the surface of the sun, less dense, kind of what you expect. You increase, you lower the temperature. Then we get to the corona of the sun, which somewhat paradoxically is 10, 100 times hotter than the surface of the sun. So this is strange. If the energy is coming from the sun, why is the atmosphere of the sun hotter than the surface of the sun? This is called the coronal heating problem. It's a big ongoing area of research. And basically the solution, as far as we know, though we haven't proven this observationally yet, is one of two mechanisms, both of which relate to magnetic fields. So either there are magnetic fields stretching through the atmosphere of the sun, which we know are there, that are vibrating really, really fast, and this heats up the atmosphere of the sun, or there are solar flares happening on scales too small for us to see. We call them nanoflares, happening everywhere all over the sun. And this is also heating up the atmosphere of the sun. So we haven't proven those yet. Both of them work in theory, as it's just about getting the observations. But basically, the magnetic field is heating up the sun's atmosphere. Yes.
Would that imply that the chromosphere has a different temperature during solar maximum versus solar minimum?
Yeah, so the ambient chromosphere, so we call the quiet sun chromosphere, is about the same. But the chromosphere above sunspots is hotter. So if you have more sunspots, I guess the average temperature of the chromosphere will be slightly hotter during peak solar maximum, but you can really split these up between quiet sun and an active sun.
Actually, I was asking you about the chromosphere.
Oh, the corona. Yes. So, well, there was someone on here earlier who mentioned, I forget the gentleman's name, who mentioned he'd seen 12 solar eclipses, total solar eclipses. The corona of the sun looks very different at solar maximum versus solar minimum. The solar maximum corona is hotter, as you suggest. There's more going on, but you can see these differences with your eyes during a total solar eclipse. So this was a very active time. So there was a lot of different structures, and it almost reminds me, if you ask a kid to draw a star, they draw like a 5-pointed star, and we say that's not how stars look, right? But to me, during the solar maximum eclipse, that's what it looked like. It almost looks like a pointy star with these big points coming off in all directions. Whereas when the sun is not very active and you see an eclipse, instead of all these different points, you maybe just have one or two either side. Looks a lot simpler. So yes, to answer your question. Yes, at the front.
On the chart, it shows the solar cycles over the many decades.
Mhm.
That all of a certain size range of sunspots or a certain minimum size?
Yeah, so the way I'll just bring that back up here. So to answer your question, basically anything that is independently sort of visible as a spot. So when you have very large active regions that can have sort of hundreds, not hundreds, but maybe like dozens of sunspots in one place, it can be trickier to count, especially back before they were using sort of, the telescopes that we have today. But to answer your question, basically any individual small spot. So if you looked for a telescope, you might see there's like one big spot and a few satellite spots. They would count each small satellite spot as an independent spot. Yeah, but sort of the definition is it's got to be classified as a spot. You've got to be able to identify both umbra and penumbra. So it can't just be sort of a dark patch. It's got to be visibly a sunspot. Yes, sir.
Have you figured out what the reason is for the linear cycle?
Yes and no. So we know the reason for the cycle. We don't know the reason why it's 11 years. So the reason we get the cycle is the sun does something called differential rotation. That sounds complicated. It's not. The Earth rotates as a solid object, right? Which means if you're standing on the North Pole, you're standing on the equator, you have a 24-hour sort of rotation, right? But the sun rotates differentially, which means the equator and the poles, they all rotate at different rates. This also happens Jupiter, Saturn, sort of the gas planets as well. So because it rotates at different rates, the equator of the sun, because it actually rotates faster, has this effect where if you imagine a magnetic field that looks like the Earth's, like this is actually pretty similar to what the sun's magnetic field looks like at solar minimum. So a solar minimum, it's close to a dipole, has a North Pole, a South Pole, that's it. And if you imagine I take this and I start winding up at the equator faster than the poles, you can imagine a scenario where I'm sort of now like coiling up this magnetic field. It's getting twisted. As I sort of twist that magnetic field is getting more concentrated and more dense. And it's as you start to compress this magnetic field, that's where you start to get these sunspots start to form, where you have that sort of concentrated magnetic field. So we know that, and then as you continue winding, eventually that complex structure winds up so much that it decreases below the surface of the sun, and then you're left with a very simple magnetic field left over again. And the pole during that 11-year process, the sun's poles actually flip. There's a full north-south, south-north flip. But why it's 11 years, not 100 years, we don't know. We haven't been able to show analytically why it should be 11 years. Yeah. Yes.
Maybe it does synchronize in 11 years. Maybe these different rotations of the polar and the equatorial rotations may somehow come together at the end of the 11-year cycle.
So that's the current idea, that, you know, some ratio of these speeds reaches a harmonic of 11 years. But we've not been able to show that analytically just yet. And part of the problem is the statistics. Like, you know, we have a few hundred years of observations, but we only have 25 data points, right, for the cycle. So it's tricky to do this. And there's also ideas. You'll also notice, as well as the 11-year cycle, the peaks of these cycles are all different. So right now we sort of have a moderately sized peak. Back cycle 19 was massive. There are also other theories that there's a larger cycle underlying here as well, maybe going from sort of cycle 12 to cycle 25. There's sort of a greater year cycle, but again, we don't have the statistics for that.
The other thing is the end of the cycle is next year, not this year. And it may go up further than what you observed this year.
Yeah, so we current forecasts are that they actually updated this about 3-4 months ago. That solar maximum we're expecting about November this year. They brought it forwards with the new estimate from what was going to be 2025. But it's a bit like investing, right? Like, or time. You can't time the market. Like I could show you this plot towards the end here. And you could look at this and say, okay, looking at this black curve, we've already reached the peak, right? I should sell all my stocks because it's going to tank now. But we don't know if, you know, this year, next year, if it could continue rising, and then I've missed the peak. So it's basically difficult to say if we've reached the peak or not. But the current prediction is November this year. Whether or not it happens early or later than that will be interesting to see. So.
When was the Maunder minimum?
So Maunder minimum was before solar cycle 0. So before solar cycle 0 here, when the astronomers who first started putting this together, they thought, okay, this is sort of where records begin. I'll start the cycle here. There were previous records, but they were sort of few and far between. And he thought, okay, you know, the records don't exist, so I'll start here. Turns out the records did exist. But before this period of 1750, there's about 60 years with no sunspots for 60 years. So there were just no solar cycles for about 6 cycles. So it was initially thought there just weren't observations, but now we have validated there were observations. So before solar cycle 0, there was a period of no sunspots at all for 50, 60 years, which is really, really bizarre. Some people were worried that this, because solar cycle 24 is so much lower than 23, people were sort of worried we'd be going into another solar minimum that would extend for decades. But thankfully, this solar cycle is already bigger than the previous one, so it's not looking likely that that's going to happen. Yeah.